Okay, so now we come to the fifth notebook, one of the most important notebooks, where we'll be studying NumPy arrays in more detail. So as usual, we'll import NumPy as NP. Now, it should be clear to you by now that both vectors and matrices are NumPy arrays. So a vector is a NumPy array of dimension 1. Matrix, we have represented it as a NumPy array of dimension 2. Okay, so let's quickly get hold of that idea and make it clear. So x dot shape, we already know x dot endim is 1, right? This is a NumPy array of dimension 1. M is a matrix now, and that's a NumPy array of dimension 2. Alright, so m dot shape is 2 cross 3, 3 cross 2, and then m dot endim is 2, right? So it's a two-dimensional NumPy array. So what we will do now is, rather than just looking at vectors and matrices, we will look at NumPy arrays in general. Okay, so it could the NumPy array under discussion could be a 1D array or it could be a 2D array, and towards the end we will see that it could even be a three-dimensional array, and we'll see that higher dimensional array are going to be really useful in data science ML. Okay, so far we have not really concerned ourselves with the data type of the individual elements of the array, but that's also important to know. So for example, let's say we have an array of the form np.array of 1 comma 2 comma 3. Okay, now there is an attribute called dtype that gives us info about the type of each of the elements of the NumPy array. So x as a whole is an NumPy array of dtype int64. Okay, this is an int64 NumPy array. We could specify the dtype explicitly also. So here I am specifying it as int32. Okay, and if you look at the dtype x dot dtype, you see that it's int32, right? Depending on what you specify. By default 64. So this is, so if you get rid of this, you get int64, right? We also have floating point, right? So 1.2 1.2.3 dot would be floats all. So the dtype will be np dot float 64. Okay, likewise you also have what are called boolean arrays. So np dot array of, so it's a list of, it's an array of boolean values. So for example, true false false is a boolean array. So this is how it look, and its dtype is bool. Okay, so these will come in really handy later on. You could also have strings. So for example, np.array of, say if you are doing a classification problem, red, green are two labels, then you could have a list of an array of strings, right? So this could be, right, and this is the d type of this particular array. Okay, now sometimes it might be important or necessary to convert from one type to the other. This is quite common. So let's say you have np.array of uh, 1 dot 2 dot 3 dot, and you might want to typecast this to, so this is what d type, this is float, right? So this is float 64. You might want to convert this to int, right? So what you can do is, is convert this to int, right? So extra dash type of int. Okay, that will give you, if you look at the d type, it's in 64. You could also specify something else. This is in general, right? You might want to convert this to int 32, for instance, in which case you can specify int 32, and that will give you, that will do the conversion. Okay, so that is as type. Next, we look at reshaping. Recall that we looked at reshaping in an earlier notebook. We can reshape vectors to matrices, matrices to vectors, and in general, you can change the shape of different types of arrays. Now, let's look at np.arange. So this is np.arange 1 to 7. So this is nothing but 1 to 6, right? And we want to reshape it into a matrix. So m is equal to x dot reshape of, you want to reshape this vector into a 3 cross 2 matrix. So what is the dimension? 3 comma 2, and if you look at m, it is indeed now the reshaped version. Okay, right? Now it's important to understand what is happening here. We could have actually reshaped it in two different ways. Okay, so in this reshaping business, what has happened? 1 and 2 have been put in the first row, 3, 4 in the second row, 5, 6 in the third row. Okay, seems reasonable. But we could also think of adding 1, 2, 3 in the first column and 4, 5, 6 in the second column. That is another way of reshaping, right? So why does NumPy do the first one, right? The one on the left. Why does it produce what we call a row major ordering, where you kind of fill the rows first or you fill the columns first? You do it in a column major style where you go one column at a time, right? So you go one row at a time, that's row major. You go one column at a time, that's column major. So let's see how we can force NumPy to do a row major or a column major ordering, right? So let me take the same, we take the same example. So this is X. Now what is M? X dot reshape. Okay. Now 3 comma 2, but then I'm going to specify the order. So if I specify the order as C, okay, then I end up with row major ordering. So this is also called C ordering. If I specify F as the order, notice that I end up with a column major ordering or Fortran ordering, right? F here stands for Fortran and C stands for C ordering. Now by default it is C. Okay, so if you don't specify the order, then what NumPy will do is it will give you row major ordering. Okay. Likewise, you can start with a matrix and convert it or reshape it into a vector. So this is 2, 3, 4, 5, 6. Okay, what you want is X, which is np dot or m dot reshape of 6, right? I just need these 6 dimensions. I just need a one dimensional array with shape 6. Okay, and what you end up with is X. You could have also done it in the following manner. So let me copy the matrix M. Okay, so X equal to M dot reshape of -1 would have also done it. So what does -1 stand for? -1 stands for the following. What you're asking NumPy to do is to figure out the dimension on its own, right? So your dimension, or rather the shape on its own. The shape here is what? 2 cross 3. So when you enter -1, NumPy will know that it has to reshape it into a 1D array of shape 6. Okay, this will become more clear when we look at the next example. Alternatively, you could have also used Ravel. So m dot Ravel. If you see what this is the same as what you saw before, right? So we could have used Ravel, so that, and the same thing holds here, right? So Ravel also works with different ordering. So you could have done a column major ordering. So you Ravel M using a Fortran ordering or a column major ordering, and that will give you 142,536. Why does it give you 142? Because it's column major. 1 4 first column, 2 5, 142 5 536, right? So that's about matrix to vector, vector to matrix. What about one matrix to the other? So you have M equal to np dot array of 1, 2, 3, 4, 5, 6, and you want to reshape it into P, right? So what kind of ordering is used here? Clearly it's row major. So you can just go ahead and do np dot reshape. P is equal to m dot reshape 3 comma 2. Okay, and that will give us 1, 2, 3, 4, 5, 6 row major. Okay, by default it's row major. We retain that. So here is where this -1. I'll introduce this -1 again. Reintroduce it. So what is happening is the following. So you have a 2 cross 3. So remember that the final product has to be the same of the shapes, right? So if your initial shape is m cross n and your new shape is p cross q, then that means m into n has to be equal to p into q, right? So that much is taken for granted. Okay, if you don't, you try to reshape it some other way, you'll get an error. Okay, so in this case, what is m? M is 2 cross 3, and let's say you are lazy and you don't want to figure out what P and Q are. But you kind of know that it has to be 3, but you don't want to figure out Q. Of course, it's very simple. Q is equal to 6 by 3, which is 2. So in such a situation, what you do is you be lazy. You can afford to be lazy, and you enter 3 comma -1, and that's an indication that NumPy has to figure out what this dimension corresponding to -1 is. Okay, so this is m dot reshape. I could have specified 3 comma 2 and I'd be done, but I don't want to figure out. I'm too lazy to do this, so I add -1 here. Lo and behold, NumPy has figured out that the missing dimension is -1. So if you now go back, when we try to reshape here, that's the role -1 was playing. So it is m cross n, and then since it's a -1, it has to be just a single number, so that has to be 6. All right. So that's reshaping, a very useful tool. Okay. So now we look at matrix vector addition. So you want to add a vector to every row or column of a matrix. So in this first example, we are looking at adding a row vector to every row of a matrix. So what is a matrix? Sorry, what is the matrix? np.array of 1, 2, 3, and 4, 5, 6. The vector is, the row vector
It's
is
6 o'clock.
1, 2, 3. So how would you add this row vector to every row of m? Actually quite simple here. It's just m plus b. Okay. So what is happening here is an operation called broadcasting. So think about this as m and this is b. So what is NumPy doing conceptually? It's kind of stretching this vector b along all the rows so that it creates 4 copies, three more copies or 4 copies in total of the vector b, and now the dimensions are compatible and you can add element wise. Okay, this is a conceptual explanation. This is not exactly the way NumPy does it because this is not at all memory efficient. You are creating 3 extra copies, but NumPy will do it in a memory efficient manner, and the process behind this is called broadcasting. Okay, so whenever you have two arrays of different shapes, okay, which you are trying to combine using some operation like plus or star, then broadcasting comes into play. Okay, so there are some rules for broadcasting, and the two arrays, the two operands on either side of the the operator. Okay, so let me repeat. This is the operator. Okay, these are the two operands. So the two operands on either side of the operator must follow certain rules called the broadcasting rules for them to be combined using that particular operator. Okay, there are these rules. We'll not go into them for now. It's just enough to know that if you have a matrix and a row vector, then when you do m plus b, broadcasting is happening, and you are allowed to do m plus b. Now let's look at the case where you have to add a matrix and a column vector. This is where things get slightly trickier. So you have np.array 1, 2, 3 and 4, 5, 6. Okay, b is np.array of 1, comma 2. Okay, can you do m plus b? Would that add b to every column of m? Let's try it out. It throws an error. So it throws a value error, and most important thing here is the error message. So operands could not be broadcast together. So that's the reason is the operands do not obey the broadcasting rules. Okay. Had this been a row vector with shape 3, things would have been fine, but this is not. Okay. So what do you do in this case? In this case, to get this working, you add you reshape b to be a column vector. So in this case, it's 2, comma 1. Okay, that's the size. So now you will see that you are able to add this column vector to m. Okay, so this is how you do it for column vector matrix addition. All right, so that takes us to what is called advanced indexing. Notice that we already know how to index into NumPy arrays. Now let's look at what we mean by advanced indexing. Let's take the array as given here, -1 0 4 3 7 8 1 9. Okay, now in fact seems to be mistake here. So let's say we are interested in retrieving. Okay, so we are interested in retrieving indices 136. Okay, that's fine. Okay, so I want to retrieve the elements at indices 136. How do I do that? One way to do that is to look at x of 1, x of 3, x of 6 independently. But then we can do better. We can pass the list itself as an index. So we can pass the list of indices into the array, and that will give us the corresponding element. So what is set 1? It's 0, and then 3, and then 6. Okay. So this is advanced indexing where a list itself can be an index. In fact, we could also have NumPy arrays themselves as indices. Okay. how does this work? So you could go inside and say np dot array of 136. So this is, notice that the array itself, an array itself is an index. This also works. Okay. What also works is a boolean array. Okay, so an array of true false values. So let's take np dot array of, so 136. So first index is false, 1 is true, 2 is false, 3 is true, 4 is false, 5 is false, 6 is true. Okay, how many do we have? 0, 1, 2, 3, 4, 5, 6, 7. Okay, so 7 is false. So this is the index. Now I can do x of int, and notice that I get the same output. So this is Boolean indexing. The whole thing is called advanced indexing. The summary is that you can index using lists, numpy arrays themselves, or Boolean arrays, which are just numpy arrays with Boolean values. Okay, so why is all this useful? We can use this to do some filtering operations. So let's look at this array, np dot array of 3, 1, 5, minus 4, minus 2, 1, 5. And we want to extract all elements that are positive. So how do we do that? We just specify x greater than 0. Okay, so what is x greater than 0? Let's first do that. What is x greater than 0? That will return a Boolean array where the corresponding element is true if the number is positive. If false, if it is not positive, it is false. Okay, now this is a Boolean array and this can be treated as indices, right? So I can now index into the original array to extract all the positive elements. Okay, now rather than doing it in two steps, you can actually do it in a single step. So this is x. Now that is all you need to extract the positive elements in x. Okay, so we could also combine multiple operations. I'll just give you one example. Let's say you have the same array. Okay, and you want to extract all positive even numbers from this. Okay, maybe I'll make this 6 and 8. Okay, now how do you do that? So you want x greater than 0. That's the first condition. And you also want x percentage 2 double equal to 0. Correct? You want both of them. This will be your, so this will return a Boolean array. Okay, this can now be your index. Notice that 6 and 8 are the positive even numbers in this array. Okay, now you could also do or. Let's see, what example do we have? So you have, let's say, an array of strings: red, green, yellow, red, yellow, green. Okay, so you want to extract. So these are the label. You can think of these as labels. So how many are there? 1, 2, 3, 4, 5, 6. So x equal to, let's say, p dot array of 1, 2, 3, 4, 5, 6. Okay. Now x dot shape. What is y dot shape? Okay, 6, 6 each, right? Now what we want to do is we want to extract all those values of x where y is either red or green. How do we do that? So y is double equal to red. This is one condition. Or y is double equal to green will be a Boolean array. Now this you can index into x, right? So you have now extracted what is red or green. So notice that yellow is the only other color, 0, 1, 2. So uh, so maybe it's easier to use 0, 1, 2. Okay, so what do I get? 0, 1, 3, 5. Okay, as expected. Now you could have also done this, since there is only one color other than red or green. So if you want red or green, that means you don't want yellow. So this is the not operator, not of yellow. That will give you this Boolean array, and then you can index into x. So that will again, that has to give you the same result. Of course, this will only work when you have only 3 colors, right? So if not, you have to stick with the or operator. Okay, so this is how and or not can be used to combine multiple conditions to get Boolean arrays, which can then be used as advanced indices.